we'll be speaking about so the title of the talk is cost-effective logging at scale, like ShareChat's journey to WarpStream, and so a bit about us, but you can read on later on, and we'll just skip directly to it. So, but before we start, like these are the people who helped us on this journey. So Brijesh is sitting right here in the audience itself, and there are other people who could not attend, but all of them helped us to because any underwear is usually a team effort, and it was only with the help of all of these people that we could have WarpStream and ShareChat. And we, as I said, like before I start, I want to ask like how many people here are aware about WarpStream, like what WarpStream does. Okay, I see a few people. So I hope this number goes up by the end of the talk. And I'll explain like what is WarpStream, why WarpStream, and what is logging, honestly. So basically, an interesting thing that we see, is that this is a diagram that is pretty like relevant for ShareChat and probably a lot of other companies who are probably doing a lot of ML workloads or ML first. And so when we talk about logging, the first thing that people usually think about is application logging. That is like your application logs that go through, and then your application logs, metrics, traces. But a much bigger data that actually gets logged is for machine learning use cases, because you need all your features, all your targets that need to be logged, that is then used for training. And the scale for that far exceeds whatever we have for application logging. So that is what we are talking about. And so basically, this is a very basic architecture of like how like an inference request. So think of it like you are using any social media app like ShareChat, or like Instagram or Facebook. So what the first thing that you do is this, when you go to the front page, there's a feed request that happens. So there will be some service that is serving that feed request. So first thing that it does is like it fetches the features, and then there is some we then process those. We do some processing, and then we send it to a model for inference, and we get back the response. So now there's one step that is critical here is that we send back the response, but in async we also log whatever we have sent back. So that is called logging step. Like we log all the features that was sent, and this is helpful much later for training. And that is what we are mostly going to talk about. And this architecture is actually called a log and wait model. And this architecture is quite common. Like almost every year we have a model deployment, like especially in REXs, recommender systems. And so when those things go to logging, what happens is that like we usually send it to any like Kafka compatible like queue. Kafka is the queuing system we use in ShareChat internally, and then we have our entire like batch like ingestion ecosystem, which is like which takes it into our warehouse. There are multiple steps here. Like it's like this typical medallion architecture, like bronze layer, silver layer, and then you have the final data store where we have like data and TF records that are used for training, and then some analytics tables as well, because you need that later on. And what we tried to do was we tried to replace this, because the Kafka, like we tried to replace our Kafka like internal implementation, whatever we had, with WarpStream. Now there are reasons for it. Like this is actual like workload from production for one of the use cases. So if you see like it is highly elastic. The workload in fact goes down a lot at night. Like all the like throws that you see that are at night, and the peak, like night as in like night 4 a.m., 5 a.m., like morning, early morning, late night, and the peaks are at like night 9 p.m. or 10 p.m. So if you have something like any stateful Kafka deployment, like be it like open source Kafka, be it like Confluent Kafka, be it any other thing like Red Panda, like all of those things are like heavy, like they are brokers, like the brokers are stateful. They cannot like scale up and scale down on demand. So usually provision for peak. And that usually results in a lot of wastage, because if you see, you have like many points in time where the CPU or the like any of the resources are not completely utilized. In fact, like if you scale it for the peak, it will always be over provision, and Kafka does not scale like natively. So, and then there will be many such issues that you will face, because you cannot. And the last part is that no matter what you have, you would have to pay a lot of cost for all of these things, not just the infrastructure, but also something like networking. So now I said, like, how many people here are aware of the networking cost that you pay in your company, like network, interzone, interregion, etc., etc. So people who are aware and they have optimized their systems from a cost perspective would know that those costs add up. In fact, if you look at like how it is in like a typical Kafka deployment, like this is a slide from that we picked up, like almost like 80% of the cost can go towards networking. And that is not like a value that we are cherry picking. and those production deployments were actually like highly optimized. And even post that, you see these things. Like you can implement things like follower fetching, and then the other things like you can, the producer, in the producer, you can have like specific strategies which will reduce those costs. But no matter what you do, you cannot reduce it beyond a certain extent. Because whenever you produce to a leader, so there can be like, in 2/3 of the cases, the leader would be in a different, let's say you have 3 availability zones. In 2/3 of the cases, the leader would be in a different availability zone. And even if you produce like to a leader in the same availability zone, it is replicated because Kafka has replication. So let's say the default replication factor is 3. So you every test twice replicated. So for each GB of data that you produce, considering a replication factor of 3 and considering that intra-AZ zone, so like you will have like this cost we picked up from like WarpStream blog, but then like you would say that there will be like 2.66 times the cost, like I would say, like for inter-AZ things. And that is just if you're thinking about like, now that it differs across cloud providers. Like some cloud providers charge you both for ingress and egress, some are just egress, etc., etc. So now WarpStream has a very specific architecture where WarpStream has full Kafka compatibility in the application binary compatibility. What this means is that you can just plug and play WarpStream wherever you have any other Kafka compatible thing. And how it works is basically there are agents that are deployed in all the availability zones, and you locally produce to the agent that is there in your availability zone. You never produce to any agent that is in any other availability zone. And in fact, because the agent then writes to S3, the replication is automatically taken care by S3 or any S3 compatible, I would say, storage service like GCS or whatever you use in your cloud storage. So by the way, we are on GCP, so we use GCS. So, and because that by default is free. In fact, like cloud providers incentivize you because that is free. Like if you write to object storage, it is thrice replicated and you don't pay for that replication cost. So that is the core, like the thing that like WarpStream does, which is what makes it like the AZ cost mostly disappear. And oh sorry, my bad. What I will do is I'll use this. So this is basically, now before I go on to explain a lot more, so there's this wonderful talk by Richard, who is like one of the co-creators and co-founders of WarpStream, and that's from Kafka Summit London, and that explains all the architecture if you want to know in more details. But I'll skip for it, and then I'll just explain like briefly like how this looks like. So we have, so this is like a typical architecture that we have. Like this is the write part and the read path, and I'll explain it in detail like how this thing works. Because like this seems pretty simple, like this idea seems pretty simple. Why not just write directly to S3 and it will work? But then the question that someone will ask is like, why has no one done it till now? Like because if it's so simple. Now you would see the nitty-gritties in deep, like if you walk through a talk and then read through the blog post. By the way, like the blog post on WarpStream website are really awesome. But one big issue that always comes is that like S3 is cheap for storage. It is not that cheap if you keep on producing a lot of like produce request. In fact, requests, like I would say any put or get requests are very expensive in S3. So what happens in WarpStream is that like by default, like the client, like the agents that we have, which are stateless, which are entirely stateless by the way. So they have a buffer, and the buffer by default, whenever you produce to it, when you produce to WarpStream, the client does not act back by default. It adds those in a buffer, and after a pre-configured period, which is usually like 250 ms or like 4 MB, this is the default, and it would write those down to the object store. And the interesting part is, like if you see about this, like all of these things are happening in a way where that is very different from how Kafka works. Now, if you load Kafka, like in Kafka you produce to a broker where the leader for that partition resides. Now all of these things are non-existent. Like here in WarpStream, like things like partitions, things like topics are virtualized. Like they're not like physical concepts that you can see. In fact, like that is all taken care of by the metadata store. So what happens is in a data layer, you just write it and that buffers and that writes it to S3. The metadata is what actually assigns you like what topic and partition, what I would say offset number you are, and then you get back the response. So this entire process actually takes some latency added to it because you are buffering and then there's a metadata call and then you get back for the whole batch you get back the response. So this would be like somewhere between like P19 would be somewhere between like 500 ms to 1 second, and that is basically the trade-off that you're putting up here. And for our use case, which we noted down, which was mostly for ML logging, we did not care as much because those then went for offline training. And for offline training, we don't care about like millisecond latencies or like even 100 ms. Like we are fine with even a second of delay. So that is how the write path works. Now the interesting part is also the read path. Like how do you think about like in this architecture where you have like agents across zones? How do you make a like a zero AZ cost like for like zero networking cost for the read path? So effectively, like in Kafka, you have something called follower fetch, which what you can do is you always read from, because every partition is thrice replicated, so you read from a partition that's in your same availability zone. So that is a similar concept what you can do here, but they go like a little bit further, because as I said, gets and puts are expensive. So you cannot, like, let's say what can happen is that there can be multiple consumers fetching from a topic, or and they might be fetching the same data. So going to S3 every time for that fetch will be expensive. So one thing that WarpStream does is like, it is like a very simple concept. Like it's like a, like if you have it's like a very simple concept, like a distributed cache. It's like a distributed, like they said it as a distributed mmap. Like if you have heard of mmap in operating systems, you know that. So the OS maintains a like a page cache kind of a thing on top of the disk, because going to a disk is expensive. Like it's something similar where you don't want to go through S3 every time. So basically all the consumer agents are in a hash ring. And one agent is responsible for, say, for let's say some partition for answer some topic. So whenever a request goes to the agent, it knows that which agent in the group would be responsible for that data, and that will fetch it and give it back to the other agent. So that ensures that the reads from, I would say, S3, like the get requests, are minimized. So both of these combined help actually minimize your costs. And it seems very simple on the top, but then consider like how would all of these work in all of your clients which implement the Kafka protocol, where like these things have to be accounted for, like the latency has to be accounted for, and then so they have like, you can like read all the blog post in more detail to learn more about it. I'll just say that because it will be too much for one talk, but I can explain like so what we got out of this. So we reduced our networking cost from something like 70% to like negligible. And now we get auto scaling with the agents. In fact, the producer and consumer agents also scale independently. You can have like different agent groups and they scale independently. And we don't have any disks for the agents, so they are like, they're running on Kubernetes spot nodes. In fact, any agent can come down, go up, we don't care, because all of the data is stored reliably, durably in object store. And again, like we have a very simple like solution here. Like there's no need for any dedicated teams, etc. There's no need for any local disks. So there are very few things that can go wrong when you have a stateless solution. A stateful solution, like if you have a Kafka in your like org, either using a like a very big managed solution, or you have like a team that is managing that Kafka setup, because Kafka can be difficult. And here, like there's no like concept of like zookeeper. There's no concept of like leader election, rebalancing of partitions and all those things, because all those are virtual. And the metadata store that takes care of all those things. And the one trade-off that you're making is that the latency will be much higher. You will not be able to get, I would say, like low millisecond latencies. The P99, because the object store latencies are high, so your P99 would be affected by the P99 of the object store latencies. So there are some trade-offs that you can take. Like I think S3 has something called S3 Express One Zone, which is much faster. You can probably try that if that is suiting to you. But one other thing is that like this is a very nitty-gritty thing, but then like the WarpStream agents are pretty network heavy. So I'll explain that more on that later, honestly. Like we can skip that. So then we go to like a deployment model that we have for WarpStream. So we actually had an architecture where we had like, the interesting thing about like stateless agents is that you can deploy it anywhere you want. And then it's a very simple deployment. So in fact, our deployment is split across two, I would say, Kubernetes clusters, because the producers and the consumers were on different clusters. In fact, we had a producer that produced in two zones. That is zone B and zone C, and a consumer that was consuming from one zone. That is zone A, I think. I don't remember exactly. Yes, the zone A. Zone A. Then look below, that's the consumer, and the producer was in zone B and zone C. So we had a one deployment in one cluster where we had the consumers deployed, and we also had a compactor agent by the way. Like, if you think about like WarpStream, there's a compaction going on behind the scenes, because when you write to S3, you keep on compacting the data to make sure that it is in a format that is easily queryable, I would say. So, and then our producer were in The consumer was in zone A. So producer was in zone A, B, and C, I think, right? All three. Or probably was in just two. Was the producer?
Producer, all three.
Yeah, I forget. Yes, it's all three. Yeah, producer and all three. Yeah. So, and what we decided on architecture was like we would have like a separate, like because we didn't have like a central team that is looking at all of these things, right? So we decided on architecture where you would have like a separate like deployment like on a namespace for each business unit that we have. Like in ShareChat, we have different business units that can have the separate WarpStream deployments, and all of them can be independent of each other because honestly, because since everything is virtualized, we don't care as much. Like even if like there's like a multiple deployments, because there are no concepts or like clusters to manage or things to do. They're all stateless. So I will leave it here, and then Vivek can actually explain more about like how we did the implementation and the best practices, and that would be very helpful for people.
Yeah. So thanks, Shubham. So I think the whole crux is like, as a company, what you should ask yourself is, do you understand your latencies well? Like low latency and all is pretty cool, but do you really require that? And if you don't, then WarpStream comes into the picture, and it's something that you can definitely try. So I think over the past year, we have been able to use WarpStream across ShareChat, and these are some of the best practices that we found out and we'd like to share. Yeah, so we'll go topic by topic. Like first we'll cover agents, then we'll cover clients, and then we'll share what are some of the recommended configs. So yeah, as we saw here, let me just go back. Yeah, so here you can see that in case of zone A, we have like different deployments for producer and consumer. So we had our consumer was basically Spark. And what we were facing was that consumer, because in case of Spark, we were like waking up every 1 minute and we were reading tons of data. So if someone was producing in the same zone, so both the workloads were getting affected, right? So WarpStream has something called agent roles. This means that you can have separate deployments with different roles, and they will also. So in case of zone A, we had to, separate out the deployments for producer and consumer. So yeah, I'll just go back. Yeah, so these are the agent roles. So there's a proxy role, which is the default one. So in this case, the agent will do reads, writes, as well as compaction. We have proxy produce for write only, then proxy consume for read only, and jobs for background jobs. So it's better to also like take out the background workers in a separate deployment, because they can run hotter than the other, because let's say your HPA for proxy is like 50%, so here maybe you can run them at 70% or 80%. Second thing is that there is no added efficiency for reading and writing in the same zone, and this is what we basically used by separating out the produce and consume agents. Because the file cache that WarpStream has is read through and not write through. Next thing that we did was we tried running the agents with spot instances instead of on demand, so that we can save some more cost. And I would suggest that you try with your consumers first, because even if they go down, then you can clear the lag. Yeah, so next important point is that a small number of large agents is much more efficient than a large number of small agents. So let's take the first case. Let's say you have 40 agents with 1 CPU each. So this means that every 250 milliseconds, which is your batch timeout, you will write 40 files. So this means more put requests, more class A operations. So it will cost more. Like as Shubham mentioned, the main cost in any object storage is the put and get API calls. And also each agent will run its own set of compactions, right? Like in case the agent role is proxy. So this will lead to more CPU and networking usage. Now let's check the other thing. So if you have a small number of large agents, let's say you have 10 agents and each have 4 CPU, then you'll write 10 files every 250 milliseconds, and this will lead to lesser cost due to, again, like less class A operations. And also there is something called cache size, which is like 0.5 GB per core. So as your cores are more, you will have a bigger cache. So this will mean that you'll have like better RPC and you'll have to go to the object storage less. The one thing that you have to note is that if you make the agents too big, then definitely there are chances that they'll be underutilized when the load is a bit low. Yeah. So next thing we have is the compression. So data in object storage is compressed, and then only it is stored. So by default, we use LZ4. So after talking to the WarpStream team, we decided that maybe ZSTD would be better. And at a slightly higher CPU, which was like barely anything. So we got a better compression, as you can see in this graph. And also we saw 35% cost reduction just by changing the compression algorithm. So this is the environment variable that you can use. And in ZSTD, there are different compression levels from 7 to 22, which you can use to tune it further. Yeah, so now I'll talk about producer agents. So larger batches is more efficient than smaller batches, right? So we saw that in the write path that all the writes are batched. So let's say if the batch size doubles, so put requests will cut in half, same logic. So the class A operations will go down. Now, why smaller batches are bad? First is that it increases the amount of load on the metadata store. So metadata store is like very important for plotting and idempotency. So everything will have to be tracked because there are more files. It also increases the CPU usage, and it also has an effect on the end-to-end latency because now the agents have to read more batches and perform more I/O. So how do we control this? So there are two ways. So first is batch timeout, which is 250 millisecond by default. And second is batch max size bytes. So it is recommended that we use batch max size bytes instead of batch timeout because otherwise every time, there is a guarantee that you'll have to get 500 millisecond, because during the write path, you'll have to wait for the batch to get accumulated in those 500 millisecond. So yeah, this batch max size is a trade-off between cost and latency, right? Because you have to wait for that size to get accumulated, but it definitely decreases the cost as your request goes down. So one thing to note is that don't do this for the agents with roles jobs because they already have like 64 MB of batch size. So in our case, this is the recommended configs. So it was like 4 GB memory per CPU, and we used a batch max size bytes of 16 MB. Now you might be imagining that how do we correctly configure these? So yeah, to know that, so whenever we write files, so there is different levels similar to what you have for SS tables, right? Like L0, L1, L2. So we have a metric which is P99 uncompressed size of L0 files. If that is approximately same as batch max size bytes, so then you can double it. And if it is less, so then you can either make the agents fatter or increase the batch timeout. So as you can see here, the P99 here is 8. And, same for here. You can see that the uncompressed file size is around 8 MB. So this is when we decided that let's go to 16 MB. And at that time, 8 MB was the maximum. After that, I think 16. I don't know what's the maximum now, but it should be somewhere around here. So yeah, this is what we noticed. So you can see that the put request went down by half. But yeah, definitely this will impact the latency. So the latency for put bytes, it nearly doubled. And also the produce latency increased. But because the end-to-end latency is 1 second, so these latency increases won't affect you that much. So let's quickly talk about the jobs agents. So as I told that they need to be throughput optimized, so they can run hotter than your normal proxy or proxy produce or proxy consume agents. So in this case, we set the HPA at 70% and kept the same 4 GB per CPU. One more thing was jobs. Jobs agents should also be network optimized compared to the other agents, right? Because they're running in the background and doing a lot of compactions. Um, Yeah. So regarding fetch, so fetch is something that might vary for you guys because we used Spark for like putting the data in our bronze layer. So we used to so the Spark job used to wake up every 1 minute and then try to read tons of data. So there's lot of load at once. So in that case, we used 8 GB per CPU instead of the normal 4 per CPU. Yeah, so let's talk about the client. So these are all uh, like you need to append these configs in your client so that, as he said, that the agent are zone aware. If you don't do this, then it won't be followed. And also we added some retries and also compression, and you can use other compressions as well, like gzip. Um, yeah, so this is the most important thing. So, so there was some we noticed that there were traffic imbalances in the agents. The reason was that the metadata max age, which is like the maximum age for cached metadata, so that was not set. So we set it to 5 minutes, and also then we also optimized to reduce it to 10 seconds, and that helped us. And also um, yeah, you can use the sticky partitioner. So these are all basic Kafka client configs, but some of them are like different for WarpStream. Yeah, so latency. So for latency, like Shubham mentioned one thing, like you can use S3 Express one if you have AWS. Apart from that, you can decrease the control plane latency, and you can also decrease the batch timeout. So as I mentioned, you can increase it from 250 to 500, but you can also decrease it up to 50 millisecond. So these are some tweaks that we can do, but obviously your cost will you is the latency. This is about latency, but yeah, it still won't be like very low, but yeah, this is something we can tweak. So about the alerts, so we added lot of alerts like CPU memory, of course, and then you have alerts on topic lag because uh, yeah, you need to like ingest from that topic. So you'll see like if the lag is not too much and like your Spark is working fine, then you have like the L0 file size for tweaking your batch timeout and all. And then you have your inter-AZ networking traffic. Uh, that that will help us to know that whether your agents are like actually zone aware or not, and how much cost you're bearing for, because this will cost you a ton if you don't make them zone aware. And then yeah, the granularity is very important. Like we had alerts based on agent, topic, as well as zone level. And also we had like uh, throughput level alert for based on like we use something called z-score, but yeah, you can use other metrics as well. So I don't think if this visible, but you can see here it's written by zone. This is like by topic. So this is all for your Kafka in-flight connections. Then you also have like CPU-based alerts. So this is zone. Then you have agent, and here you have like deployment level also. So then you have like topic level alerts here. And then you also have like compaction, object storage, how you're like, how many bytes you have in the cache, and all those things. I mean, these are all alerts. I mean, you can add more as well. Then you also have alerts on cache, on networking. I think networking is very, very important. You should definitely have that. Yeah, so let's come to the interesting thing that, I mean, WarpStream claims that it's much cheaper, but how cheap? So we did a comparison with single zone as well as multi-zone Kafka deployments for the same workloads. So yeah, in case of WarpStream, so we are just talking about ads here. The compressed throughput was around 400 Mbps, and then this was your cost. So I mean, this comes out to be 35K INR per day per Gbps. Um, so then we did the same thing for multi-zone. So here our Kafka deployment was deployed in 2 zones. And the cost was around 88.5K INR per day per GPS. So this is only for max throughput, but we also have for mean throughput. And I'll share the percentage difference as well. Then we did for single zone. So basically we just removed the inter-AZ or NICE cost, and then we did the same comparison. So it was 48K INR per day. So to summarize, compared to multi-zone Kafka, we got a savings of around 58 to 60%, and this is excluding the licensing cost. I mean, for those of you who know about licensing costs, so that's a different game. So this is all infra costs that we saved. Then for single zone, you had almost 20 to 25% cost savings. So for people, I mean, there are a lot of blogs that you can optimize Kafka to the brim and like, you'll save this and there's no added efficiency. There's still a good 20-25% to make here. Yeah, so we'll quickly also cover what Spark configs we use. So the good thing is that WarpStream has all of these configs on their blogs as well. Like, so we use the Java client for Spark. Apart from that, these are some of the changes that we did. So I think Brijesh, he was very instrumental and he was taking care of this. So first is to like maximize the parallelism. We tuned the partitions and we made sure that each partition does not process more than 1 Mbps. And then your number of partitions should be a multiple of your executor cores. And also to avoid too many fetch requests, we changed the max pole records and max fetch max byte depending on the volume of data. And as you can see, like we were able to decrease the time it took from 22 minutes to let's say 50 seconds. So these are all config changes. Yeah, so just to conclude. So yeah, so first thing before all of this is that understand your latencies, understand your workloads. Maybe you don't need that low of a latency that you think you need. Also, like for logging, observability, and data lakes, I think WarpStream is a very good alternative to Kafka. So the trade-off is between latency and cost savings, as we saw. And also like operational simplicity, and there are currently more features. Like you didn't need to worry about K-raft or leader elections, partition rebalancing, hotspots, because the agents are stateless, so they will automatically scale up or down depending on the throughput. So doesn't matter how elastic your workload is. Then all of the hard problems are with object storage, so that's like added efficiency. And yeah, definitely the cost savings. So there is another, so something was announced yesterday, it's called diagnostics. So all of the configs, everything I've talked about, so they will be provided to you in the WarpStream console. So basically it will analyze your cluster and it will tell you that how can you, like let's say you can increase the batch max size bytes, or you can, your agents are not zone aware. So all of those things, this diagnostics tool will itself point out. But anyways, I mean, we didn't know it was about to get released, so yeah, not our. So yeah, this is it. We are happy to take your questions.
So WarpStream does not ACK your produce request until like you get back, you write durability to object store. So if you have configured something like ACK equal to all, so your produce, like ACK equal to all, you know that when you get back the produce request, the response is getting back, it is written to object store. And if not, we also have, as I said, like we have retries. So if agent goes down, it will have a timeout and it will retry. Like the client will retry, and then it will probably go to some other agent which should not go down. So
I guess my question was mostly regarding the pod crash, because in the Kubernetes cluster, pod can come up and goes down
Yeah, that
I
is
mean,
fine,
at
right?
any time,
Because even if the pod crashes, like your client will retry because it's a timeout, like a produced timeout. Post that produced timeout, you automatically have a retry.
So you are basically not using the ephemeral storage with the pod, but something, I mean, kind of persistent volume, right?
Sorry, I could not hear you.
I mean, what I mean to say that when the pod crashes, the persistent volume, uh, are you using persistent
There's no
volume or?
persistent volume here. It's all written to object store. So effectively, the agents are stateless. Even if the agent crashes, so the agent will not send back an ACK, like because it is not written to the object store. So your client will automatically retry. So it will go to some other agent, and that will then write it to
Okay,
object store.
okay,
Yes.
got it.
Yeah,
Yeah.
it just has a cache. I mean, there's no storage.
Yeah. So my question is to Shubham. When you're comparing Kafka and WarpStream, you had one point listed where the infrastructure, WarpStream is infrastructure heavy. Are you talking about the number of IPs that it gets used when you bring up new agents, where Kafka will have only 3 IPs used as a broker?
Or the networking heavy part, as you said.
Yeah, the
Yeah,
last point.
I think it's a bit of a, like, we can probably ignore it. Like, I would say that you would say that it is better to use network optimized instances because the agents are doing a lot of reads and writes to S3, and there will be a lot of networking overall. So it's a minor point. It's not related to that actually. That's why also I
Like
skipped over it. Yes.
Yeah, so the major networking is because in object storage, you know, uh, sending data from one zone to another is basically free. So heavy lifting is done by object storage. This is just for metadata. Let's say you want to know, okay, in which, like, in the read path, you can see, right? Like we are saying that, okay, we want partition 1, and we want to like read 1000 records starting at offset 306. So the metadata store would tell it that, okay, you can read it from file 900 followed by, let's say, file 806. So now it will check, okay, which agent and like which agent's cache might have these files. So the other agent which got that, request, so it will try to communicate with this agent. So this is the max networking you have.
I can probably explain another way. Like, think about it like when you have like Kafka, you write to a disk, so your disk gets saturated. Here everything is network because you write to S3 or read from S3. So it's like network that gets saturated before that because there's no disk. So network would get saturated. So use network optimized instances.
Yeah. Hi. Hey. So, aren't we just shifting cost from inter-broker communication to putting data to object storage? So, how would the benefit come along?
Yeah.
How would the
How would the benefit come? So, in a Kafka setup, we would have inter-broker communication that would occur the network cost, right? Here, we are putting data from machines to object storage. So, just the network it's changed, right? How the cost is realized, like how the benefits come along.
So you're saying that, let's
Cost
say,
benefits.
object storage starts charging for that.
The transfer to object storage. So if I got it correct, we were talking that inter-broker communication is reduced because we are not replicating the data. Now we are putting it into S3, right? But okay, that inter-broker communication is not happening, but the data which I was writing to a disk is now being written to an object storage. So that network cost is still happening, right?
Actually, no, because like the object store is written in the same zone. So like you write to this, let's say I'm writing the agent in zone A, the object store is anyways replicated, right? So you write to the object store in zone A. So there's no cost that you have to pay. There's no SKU charged apart from a put. Now, if you instead, let's say, assume this was Kafka. This has 3 nodes, Kafka nodes. So if I send to A, then it will be replicated across here. So there's an SKU charged for interzone egress and probably for interzone ingress. And then let's say I am an A, but because the leader is in B, so I have to send to B. So then there is another ingress egress here, and then it is replicated, so that is another ingress egress. Okay. So you're not paying any of those interzone egress and ingress costs. Because that is how like cloud economics work, I would say, yes.
Good. So another question, since it's stateless, right? If I can just replicate my object storage, let's say if I have a production setup, and I can replicate my object storage to a testing setup, I could set up a similar cluster there. Is it true to assume that?
I mean, you're saying that you want to like use a custom storage layer.
So no. Let's say in one of our higher environments, you have a lot of data where you have a WarpStream cluster. So your data is in all your data is in object storage. If now I can replicate this object storage to a different bucket, let's say in a different environment, so I can create again a new cluster there using those objects.
Yeah, I mean, because the agents are stateless, I mean, how will it matter?
It should be achievable, right?
Yeah.
Okay, thanks.
Hi. S3 or any object store has some limitation on prefix search. So if I have a high number of consumers.
Unable to hear you. Can you repeat it, sir?
Hi. Any object store will have a limitation on prefix search. How many requests you can do based on prefix, so search or get. Now, if I have high number of consumers for a given topic, have you observed that limit to be breaching or something similar issues?
So I mean, on the fetch side as well, like you have your cache, right? So what it does is it doesn't just load that specific data that you request. Data that is in or around that is also fetched. Like it loads lot of data into the cache. That's where like per core, like we saw like 0.5 GB per core. So that's why having fatter agents is better. So you load lot of data at once, and those requests can also be served from the cache itself. So it's like smart in the way when it loads data from object storage.
Okay, thank you.
I can also give like another analogy. If you have used like a database, like you have something called a buffer pool, because you don't want to like fetch from the disk. So think of it like there's a S3 is your disk, and the consumer agents, like the hash ring is like your buffer pool. So effectively, whenever you fetch it, you keep it like there's a cache there. So because like in Kafka, you're always reading the latest data. There would be a good cache hit ratio there, and that helps you a lot.
I have another question. So what is that L0 file cache you're talking about here?
Yeah. So whenever you write your data in compressed form, the initial files that are made, so they are just called L0, and then when the background jobs run and compaction happens, so you create L1 files and then L2 files. So similar to how you have seen like in NoSQL databases, like they create layers of SS tables, right? So on the top you have L0, then L1, L2.
L0 files you mean on the object store itself? That's what you mean by that? Oh, okay, cool. And what is that metadata store here? Where does it sit?
Yeah, so metadata store, the like main purpose of it is like ordering your writes, and also for idempotency, like let's say your agent goes down, and because it's stateless, let's say it comes back up again. It processes the same write request again. So you don't want to write it twice.
The question was about which is that. Is it a persistent store, or what exactly is it? Where does it sit?
That I think that's like the secret sauce of WarpStream team.
They don't. I mean, you guys okay?
Yeah, I mean we don't host it. Like metadata store is something that they provide.
But I would say like it would be probably something like Foundation DB, because Foundation DB is consistent and it provides you like all the things that you need from like a good, consistent like database, I would say.
So some persistent then.
Yeah,
Okay.
but it's a database. Like you don't care as much. It's just they are doing the bookkeeping for you, I would say. WarpStream team.
Another question is agents can be across multiple AZs, right? So what you told about the buffer pool, it can fetch the data from the other agent, right? So that would add to your network costs, if I presume.
It actually won't. It will always fetch from S3 and like the hashing is, I would say, per zone.
Per zone itself?
Yes.
Okay,
Yes.
cool. Thank you.
Hi. Thank you guys. It was a nice talk. The one key takeaway that I got from this is like choosing the application, because when I read 70% of your costs will get reduced with WarpStream, it's not for all Kafka implementations. Some implementations which latency is acceptable.
Yes.
Okay. So now I heard like Confluent has acquired this WarpStream.
Yes.
So is it also part of you guys are using from Confluent, or you implemented when it is not bought by Confluent? Like, is it a separate software kind of a thing that I need to implement on my clusters, WarpStream versus Kafka?
So that is, I think, more of a business side of question. I mean, you can talk to the WarpStream guys, you can talk to the Confluent guys. They will able to like answer this. But
Thank
yeah,
you.
we used it before it was acquired.
Before it was.